Julia.
Yeah. So welcome everyone. Thank you very much for being here, and it's a great pleasure to introduce our speaker today, who is Steve Sain, who has a very rich experience of working in environmental statistics from all different perspectives. And I'm very happy that Steve agreed to give a talk at this webinar. And I'll give floor to Ignacio, who will say a bit more. Thank you.
Thank you so much, Julia. It's a really pleasure having Steve here. This session of today's webinar consists of 40 to 45 minutes presentation and 10 to 15 minutes for questions and answers. We suggest attendees to ask questions at the end of the presentation. And as Julia mentioned, we are so glad to present our today's speakers in this TIES webinar series on data science for environmental sciences. Steve Sain is a senior principal data scientist at senior director geospatial and data sciences. Prior to joining the team at Jupiter, Steve held faculty positions in statistics and applied mathematics and worked in industry as a data scientist, where he led research and development programs and data science teams. He has a lot of experience in different aspects from industry to academia. And now Steve is an affiliate faculty in the University of Colorado Department of Applied Mathematics, a fellow of the American Statistical Association, and past recipient of the Distinguished Achievement Award from the American Statistical Association sections on statistics and environment. Dear Steve, thank you so much for accepting our invitation and making time out of your really busy schedule. Welcome.
No, not at all. Thank you very much for the invitation. I'm very happy to be here. It's not often that I get to interact with this group. I love this group. I have for a long time, and so this is a real treat. Hopefully this will go well, and we can talk a little bit about the things that I've been doing recently in this growing field of climate risk analytics. Let's see. So I should probably go back to sharing my screen. How are we doing? Does that work?
Yeah, that works perfectly. Thank you.
Okay, great. Thank you. So I wanted to start just by setting the stage a little bit. As many of you probably know, the latest IPCC report has been coming out over the last year or so, and this is something that caught my eye in the report from Working Group 2, which is on impacts. And I'm not going to read the quote here, but basically they're making the case that the climate change is happening now, right? It's already caused widespread impacts and damages to lots of different areas. The figure I show here is just cut and pasted straight from the report. I don't know how easy it is to see, but on the rows you have different geographical areas, and the columns are sort of different impacts to different segments of whatever you want to call it. The first few here deal with water scarcity and food production. The middle ones are impacts on health and well-being, and the last few are on infrastructure, cities and other built infrastructure. And not to dive into that too much, but I look at that and I just see all these minus signs running around everywhere, right? So this just goes back to that idea that climate change is happening now, and there's widespread impacts, negative impacts of climate change. Next, I've been looking at these graphs for a while now, since I discovered them a couple of years ago, but NOAA has been tracking the number of US billion-dollar disasters. I mean, it's a great headline, but it's a terrible headline. One thing we clearly see from this is, since the early 80s, the number of these really expensive climate-related disasters just keeps going up, right? And the cumulative costs keep going up over time. A little bit further, this caught my eye in last fall. It was a blog from the US White House talking about the rising costs of extreme weather events. And it was, it cited a number of different more economic focused studies. But the one that caught my eye here was that a discussion of a traditional view of these large scale weather disasters, that they tended to be one-off events, and that there would be time for society to rebuild whatever damage had occurred, potentially even improve that damage. Not too long ago, where I live in Colorado, my neighborhood was struck with one of these billion-dollar disasters. It's called the Marshall Fire. It was a wildfire driven by drought and extreme heat and high wind. And a year and a half later, and I have many empty lots in my neighborhood from houses that were basically burned to the ground. And it's going to take years for those houses in the local economy to recover. And that was sort of the point of this particular article, that this old idea that these were one-off weather events, and not only could we quickly recover, but we could recover even better, may not really be the reality. That there's actual evidence suggesting, for example, if you look at the figure on the right here, that the impacts from tropical cyclones are taking decades for the local economies to actually recover, and they may not ever actually recover. Then you couple in sort of this idea of an increased frequency, severity, duration of these events, and we have potentially a very worrisome situation. This was an article in the local paper, also from the fall, that was sort of talking about migration and people who were moving around in the U.S. During the pandemic, and how they were not necessarily moving, or they were moving to places that you might think would be more susceptible to problems in climate change. And there was sort of a great quote about people moving in the wrong direction and markets actually underpricing climate risk. And that's going to be kind of a theme as we move forward, trying to really get the right information so that we can price climate risk correctly, and that we can actually do things that are actionable on climate risk. The second part of this article was really interesting because Redfin, who is an online real estate brokerage, did a little study where when people logged onto their website and they looked at properties, they did one of these A/B test kind of things where sometimes they would show people measures that would give them some sort of idea of the flood risk for that property. Sometimes they didn't. And they did see dramatically different behavior in the different groups in the study. Those that actually got the flood risk decision or information made different decisions. And so the takeaway from that was, there is a need for understanding the real risks that we face from climate and climate change, and that we would use that information. This was sort of reinforced in an article in Nature Climate Change that came out around the first of the year, that talked about the overvaluation of the U.S. housing market, potentially, to the tune of a couple of $100 billion. And that a lot of this overvaluation, occurred maybe in coastal areas. Florida, for example, was one of the worst. And a lot of it just simply had to do with not pricing climate risk correctly or appropriately. And the real fear here is this isn't like more typical sort of housing booms and busts that are fairly short term, and over 30 years or over decades the housing prices would always recover. This is sort of something that isn't likely to be temporary. So this is a bubble that when it bursts could be really, really bad. And the other aspect here was this article cited even more of a need for accurate and accessible information on flood risk. And so hopefully that's sort of hopefully starting to put in your mind a little bit about where we are, right? We're in a situation where, climate change isn't some far off mid or end of century problem. It's a problem facing us now. It's expensive. It's going to be even more expensive, however you want to measure it, whether you're thinking about the financial risks or the human costs. It's going to be very, very expensive. And then the third aspect of it that is that, people want to have information about what these risks are, and actionable information so that they can make reasonable decisions. And all of this is sort of made, hopefully, since I work for a startup, the market created a market for what we'll talk about as climate risk analytics. We'll talk about that for a little bit, and then we'll dive into a couple of case studies about how we actually are producing sort of the physical risk data to support climate risk analytics. And then a little bit at the end, I get asked all the time, what do people what are companies doing with the data that we're providing them? And I'll end with a couple of examples. So with all of that introduction, we kind of think about where is the market. And it looks a little bit like weather services a couple of decades ago, when we were sort of moving from simply having national weather services, government-sponsored agencies who provided large-scale forecasts. And many times these were provided really to provide warnings for extreme weather or extreme events. And many companies, many other things were really clamoring for more detailed information, hyper-local, very specific weather forecasts. I'll give you an example. I spent a few years working in digital agriculture, and the very first thing farmers or growers want to know is they want to know, what happened on their fields yesterday, what's happening on their fields today, right? In terms of weather. Is it raining? Is it dry? How wet are my fields? Can I work on the fields? Whatever it is. And that's a sort of a level of specificity that large-scale forecasts generally can't provide. And the company that I work for constantly wrestled with, do we try to build this kind of hyper-local specific weather forecast in-house, or do we go buy these forecasts from this like explosion of companies that were trying to provide them? So we're sort of seeing that now, and that's, like we were just talking about earlier, providing the right kind of information for companies to make decisions. They're realizing that the climate risks are real. They're going to have to do something, and so what do they do, and what kind of data can they do it with? So I don't have a great definition of climate risk analytics. I kind of think of it as a simple idea of actually quantifying or putting some value to climate risk, and understanding how that climate risk is evolving with the different scenarios about climate change into the future. So this could focus on flood, it could focus on heat, fire, whatever you're worried about. It's really trying to understand that risk and how that risk is evolving. We typically break that into two different parts. There's sort of what we call physical risk or transition risk. Physical risk typically refers to the risk that is direct impact from climate events. So they might be acute events like a tropical cyclone or a hurricane, or chronic events, which is thinking about longer term impacts of, say, rising temperatures and increasing drought and things like that. Transition risk is a little bit different, and that's trying to understand the risks from moving from sort of our current energy infrastructure to a more carbon-free economy. An example there might be thinking about your distribution network, and maybe you use trucks to move product from warehouses to stores or individual customers, and moving that distribution system from diesel trucks to electric vehicles. There are risks and costs to that kind of a move, and trying to understand what those might be. That's an example of what might be a transition risk. These risks sort of have a lot of different aspects. Probably the one that we're probably doing more with is in understanding different portfolios, whether we're working with banks in the financial sector that hold say mortgages on a number of homes or businesses across the country or the world, actually, and trying to understand what the risks are to that portfolio. But it could also think about companies trying to understand risks to their supply chains or their distribution networks, or even a utility thinking about their power distribution and transmission networks as well. So anything where there's collections of locations across a geographical area. and really trying to understand, how to value those portfolios, how to think about, how those values might change in a changing climate, to actually then maybe thinking a little bit about how do I mitigate loss, right? How do I, reinforce my warehouses in port cities to better withstand sea level rise and flooding. So it might be everything from pricing to sort of those engineering questions. And then there's a growing need for data to meet the regulatory response. This is being led a lot in Europe, but even here in the US, the SEC is getting ready to put down some guidance that will, I'm sure, be all over the news and fought in courts and everything else. But companies are being pressured to start reporting, their climate risk to their facilities. One brief plug here for my company and kind of what we do. Probably our biggest product right now is what we call Climate Score Global. It's a global product, high resolution, really could be thought of as a major downscaling effort. We'll talk about what that means in a minute, focusing on a bunch of different perils, flood, wind, heat, the kind of the standard stuff, severe weather, even changes in cold. And it's really designed to get at that facility resolution within a portfolio. So you could actually say something about your manufacturing facility, your power generation facility, your warehouse, or possibly even your home. And with a planning horizon under a bunch of different climate change scenarios out at least 50 years. Usually we go out to the end of the century, but most of the traction sort of in the next 50 years. Okay, so let's dive in a little bit to sort of this idea of downscaling, right? So there's kind of, when you're thinking about climate risk, there's sort of emerging, two different approaches. One is a more traditional approach, that's the top-down approach. I've done studies of this type many times, and it basically starts with the output of global climate models. You downscale the output of those global climate models, and you sort of plug the downscaled output, this time series, into your favorite impacts model. Maybe it's a hydraulic model or a public health model. And then you look at that output and you try to assess how things are changing. That can be contrasted to what's called a bottom-up approach, which is more focused on thinking about the vulnerability and then looking for those vulnerabilities in downscale climate. So maybe go back to the ag example for a minute. A top-down approach would be to sort of take the downscale climate model output, plug that into some crop model and try to understand how your yields might change over time. The bottom-up approach would be, say, go and look at your yields on your fields, say, in the historical record, and say, wow, when these certain weather conditions happen, high heat, low precipitation, or maybe high precipitation, whatever it is, my yields drop by 20%. And then I go look into the downscale climate model output and say, well, how often is that particular event going to occur? So two different ways of looking at it, but the common thread is the role of GCMs and downscaling those GCMs to an actionable resolution. So real quick idea of a GCM. GCMs are amazing pieces of technology that actually incorporate, cutting edge science, cutting edge computation, and it really are they can be thought of really as sort of virtual laboratories to study the Earth's climate. They typically look at the processes in the atmosphere, the processes in the ocean, the processes on land, and how these different processes interact to produce basically weather, right? So that's really what climate models do. A numerical weather model will start with the current state of the atmosphere and then use physics to march out hours and days into the future and give us forecasts of weather. A climate model also simulates weather, but it simulates weather over a long period of time and how that weather is going to respond to a different climate forcing. One of the emission scenarios, for example, how are the greenhouse gases changing? And then from that long time series of weather, you can sort of infer climate parameters and how the climate is actually evolving. The challenge, however, is GCMs are still very coarse scaled resolution. I often use the example of where I live here in Colorado. I live on the Front Range. You know, it's called the Mile High City. So we're at what, 5,000-6,000 feet of elevation. You know, it's maybe kind of a semi-arid climate. My favorite ski resort is Breckenridge. It's about 90 miles from here. It sits around 9,000-10,000 feet up in the mountains. Very, very different climates, but they would be within a single grid box of a climate model. So, you know, if we try to use the raw GCM output, we would be using the same time series, whether you're a scientist focused on snowpack in the mountains, or you're a water manager in the city of Denver thinking about drought and irrigation and everything else. So there is a spatial scale mismatch between what's coming out of the climate models and the scales, the spatial scales needed for some sort of local impacts analysis. I'm not going to talk a lot about bias correction today, but climate models are of course biased for lots of reasons. Again, don't have really time to get into that, but that has to sort of be dealt with. And usually the process is you take the GCM output and you do a bias correction downscaling step all at the same time to get some sort of local climate model output. Typically done in two different ways. There's dynamic downscaling, in which another, what's called a regional climate model, is used to downscale or produce high resolution climate model output, generally over a specific geographic area. Or you can use statistical downscaling, which basically turns it into a statistical prediction problem that we'll talk about just in a minute to do the downscaling. So, for example, this is an image I produced, you know, a long time ago when I was working at NCAR on a fairly large scale regional climate modeling project over North America called NARCAP. And the idea here is inside, you know, this funky shape is sort of the domain of interest, global climate modeled output on the outside, and on the inside you can see sort of the finer resolution output of the RCM. But basically what happens is the way a regional climate model works, it has to take output from the global climate model to constrain things on the boundary, and then produces sort of the high resolution input on the interior of the domain. And this is sort of naturally leading to that top-down approach, because you're sort of taking every time step that's coming out of the global climate model, and the regional climate model is marching along with that, producing the higher resolution output. A statistical downscaling approach starts by, you know, thinking about building a training set of, you sort of have historical coarse scale images, if you will. Then you also have corresponding fine scales. You sort of need this high resolution target, and then maybe coupled with information about elevation or other aspects, static aspects of the region that you're looking at. Combine those together and really creating a supervised learning problem, a regression problem, if you will. And then you know, once you can kind of think about it as a regression problem, you can kind of plug in your favorite, you know, regression or machine learning variant and produce something that operates much the same way. It takes every time step of a global climate model and downscales that time step. And then that downscaled output can be used in a subsequent analysis. There's plenty of advantages, disadvantages. Probably not going to say much here, except dynamical downscaling. The primary advantage is, again, it's bringing in all the science and the physical principles. The disadvantage is it's just almost as computationally intensive as producing the global climate model output, and that oftentimes rules it out. Statistical downscaling, on the other hand, can be very cost efficient. Although you're sort of making some assumptions about, you know, this empirical mapping from the coarse to the fine scale, and then crossing your fingers and sort of hoping that holds into the future climate. But there's pluses and minuses in both. And, there's some outstanding products in both cases. So just to talk a little bit about what we do for downscaling, it's a little bit different. We still start with the global climate models. We try to pull in as many global climate models as we can. For a long time, we worked with what's called the large ensemble. Lately, we've been moving more to the CMIP6 models as they've become available, bring in as many observations and reanalysis data sets as we can to do that bias correction step that I'm kind of waving my hands over. And then, we do some sort of downscaling, bringing in, as I said, static data sets. A lot of those derive from the DEMs, because that's really what you're trying to get is sort of the local topographic response. And then we spend a ton of time on V&V. Really deserve to talk more about that, but I don't have enough time. But the key difference is we're not downscaling sort of the every time step that's coming out of the climate model. We're not downscaling the weather of the climate model. We're downscaling the climate coming out of the climate model. So we're thinking about how do we downscale sort of the climatological characteristics of the output of the climate model. And that's a really big difference between the traditional approach and the way we think of downscaling. So for example, we might go grab every observation, MET station we could grab all over the world. We're going to do a lot of checks on the quality of those data sets, the amount of data that's available at each individual data set, or at each individual location. And then we might fit, some sort of distribution to that data for every MET station. So in this case, the figures you sort of see here is a precipitation figure. So maybe we're fitting a GEV distribution to that precipitation data. And then we're basically doing the same thing on the coarse scale data set. Maybe it's a reanalysis data set like ERA5 or a climate model data set. But ultimately, we're sort of matching these distributions up in space. And that's what gives us turns it into a supervised learning problem. Because we sort of have, the climate characteristics on the core scale lined up with the climate characteristics at a given MET station. In this particular case, we tried a lot of different, took a traditional sort of machine learning approach, started with linear regression, also brought in a lot of these sort of boosting algorithms on trees, and then some meta estimators that try to go at and combining the output, trying to get the best of both worlds, if you will. But as I said, kind of traditional machine learning ideas, a very basic feature selection. I mean, I know there's a lot of hype in machine learning right now. If you just chuck everything in and it figures it out, I've never really bought into that. I think feature selection is still a critical part of trying to build regression or machine learning kind of models. Generally, we'll start with ERA5. Also bring in, as I said, static distributions, say from the DEM to better understand the topography. We also bring in a lot of other remotely sensed observations, other climatological features, land cover, anything that we think that is going to sort of affect the sort of local climate characteristics. Throw those into the mix to try to come up with sort of the best selection of features. Cross-validation in these kind of settings is really a challenge. We tend to try to rely on a variant of a spatial cross-validation, where we divide things up into different regions to do our cross-validation. Excuse me. And then, then we're basically looking at performance. And in this particular case, some of these stacked estimators, these meta estimators, where we're combining information from both regression and gradient boosting trees, seems to perform the best. And basic takeaways are that the stacked estimator can outperform a baseline regression estimator and actually beat the raw ERA5. So in some cases we can improve things by, in this case, precipitation can be improved by as much as 40%. it just really depends on kind of the location and what we're actually trying to pull off. But to get some sense of sort of the final idea here is a number of days above 38 degrees Celsius in a year. So trying to get at, that extreme heat. Let's see, this is where is this? It just escapes me at the moment. I apologize, but you can kind of see how we go from, say, the raw RF5, which is the core scale baseline, to a much improved sort of resolution in the downscale image. You see better ideas of the coastline and the local effects for the heat metric. This is a precipitation 1 day, 100-year return level on 1 day total precipitation in the Pacific Northwest, and now you actually are getting a more accurate representation not only of the local waterways and the land surface, but this is a really complex terrain, and so we're getting a better job of bringing that terrain information in. And then over the UK and thinking about sustained winds, and you really get the sort of the same picture that by doing the downscaling, we get a more accurate representation of the local behavior of the winds, which is going to actually make sort of the next phase of any sort of impact studies look a little bit better. Switching gears entirely, this is sort of a new part of what we're trying to do, and that's thinking about the compound hazard question. And really it goes to, when we're thinking about environmental risk, it's never related to a single peril, right? You think of a hurricane, that's the biggest one we're thinking about here. Tropical cyclones, the damage from tropical cyclones comes from, not just the winds, not just the storm surge, but sort of those two things sort of acting together on the local infrastructure. And all too often, risk assessments are sort of framed one at a time, and we've been guilty of it, but we're starting to think more about how these compound risks come together. And when we start talking about loss and thinking about loss, we actually need these inputs. We need the multiple inputs, and the fact that they're oftentimes heavily correlated. So we're starting to explore how we build sort of these multivariate extremes models. This was just a quick pilot estimator, a proof of concept, if you will. We drew a very small data set between Houston and New Orleans along the Gulf of Mexico. It's a 90-meter grid. We have about 1,500 synthetic hurricane tracks. We've got an in-house model that does take simulated hurricane tracks. I'd love to spend more time talking about where that data comes from, but I'm afraid that would be again no time there. But we have sort of current and some future years under a fairly aggressive climate change scenario. Just to sort of look at what the information we're seeing from these tracks, hurricanes are sort of crazy dynamical things to model, because their behavior changes quite rapidly as the hurricane hits the coastline. So here, if we, on the top range of plots, this is just wind speed, and you see the pretty high sustained winds when the hurricanes are in the ocean, but as soon as they sort of hit the coastline, the storms start to disintegrate, and wind speed starts getting more highly variable. So there's almost this hard break at the coastline, and then trying to understand how the hurricane is starting to break apart when it goes inland. The same thing happens in the bottom plot on precipitation. Pretty low precipitation actually when you're in the ocean, unlike wind speeds. But then a big dousing as soon as those bands from the hurricane hit the land. We get a serious dropping of precipitation, and then as the hurricane moves inland and the storm disintegrates, you get a lot of variability. So trying to model these things in space and time is actually pretty complicated to do, but we're going to try. So in this case, very simple, nothing super fancy here. We just popped a Gumbel distribution, partly because we didn't want to have to deal with the complexity of the GEV in this case. So Gumbel marginals, Gumbel precipitation, and then basically using a simple cupola idea Basically, in this case, a gumbel cupola for simplicity, because there's a single parameter to sort of tie these two distributions together. Then what we wanted to do is look at the variation over space. One of the things we were really focused on or trying to understand better is how the correlation between wind and precip, in this case, evolved over space. So we actually did a lot of work to try to put some sort of regression on both the scale and the location parameters for the gumbel, as well as this cupola parameter, using different predictors, such as something derived directly from the DEM, which is the surface height, roughness length, which is a key component of the hurricane model to think about how the hurricane winds and things behave, and then just some basis functions to try to go after the variability or that discreteness, that discrete change that seems to happen right on the coastline. So sort of pulling some of these ideas from using basis functions in a spatial regression. MC the heck out of it. And at the end of the day, you start getting answers that look like this. And trying to define a return level or for a particular return period is challenging enough. When you're in the bivariate case, for example, now we have contours and we have to think about, is one extreme, both of them extreme? And so you sort of get very different representations of what the return levels look like. But in this case, you can end up, sorry, I'm not controlling my mouse very well, but you can end up getting different contours. And probably the punchline here is this is a particular location that we were interested in trying to understand how these return levels evolve from 2020 to 2040 to 2080. And, right off the bat, you sort of see the increased severity, especially in the precipitation. The precipitation is, the 200-year return level for precipitation is definitely rising. We see a little bit of increase in the wind. So there's sort of two ways of thinking about that. Either the 200-year return is getting bigger, or you can kind of think of the return period getting smaller. So you get the same amount more frequently. So anyway, this would be a nice, as I said, ideally inputs to a loss model. So very, very early phases research for us at the moment. Talking a little bit about applications for a minute. So I get asked a lot, okay, you produce all of this data, what do people do with it? For example, this was a study done by the International Energy Agency's World Energy Outlook, a report that just came out recently. They highlighted 4 locations, a coal-fired plant in India, a gas-fired plant in Vietnam, a refinery in Northern Europe, and a refinery along the US Gulf Coast. These are pretty modest scenarios, 2.6 and 4.5. 8.5 is more the more extreme scenario. But bottom line is they're sort of seeing losses in asset value as you sort of move into the future. And one of the big takeaways from this was a study of looking at flood defenses. The U.S. refinery on the U.S. Gulf Coast has flood defenses built in, levees basically to try to prevent flooding. If those levees didn't exist, the impact would be 4 times as much. So the losses would be 4 times greater. And the impact here was really thinking about, using this kind of data to motivate how you would possibly use flood defenses to try to minimize the impact. This is a different way of thinking about it, but Guidehouse is one of our partners, and they're a consulting firm who works in the utility world, and their idea is to take these kind of this kind of physical risk data, study a utilities infrastructure, understand those vulnerabilities, and then make adaptation recommendations. And so this is kind of an interesting little exercise. It's entirely hypothetical, but they chose this hypothetical utility. They looked at their transmission structures, their substations, their distribution poles, and they looked at the impact of flooding, of wind, and extreme heat, what those risk assessments over time would look like but then took the next step in thinking about, okay, how do I build resilience in my transmission infrastructures or my substations to try to minimize some of these impacts. So that's one way of thinking about it. This is kind of an interesting one because you're starting to see more of these. AstraZeneca has been using some of our data to do their climate risk disclosures. And basically all that is thinking about what is their climate risk. This is a report you can find online. AstraZeneca did a detailed analysis of, I think this is about 30 locations across the world that looks at distribution centers, manufacturing, R&D, and sort of tries to label those facilities and what their climate risk is. That's the top plot. In the bottom graph, they actually are looking at exposure in their supply chain. So they took 10 different medicines, look at their supply chain facilities, identified the risk, their present day risk on the x-axis, and sort of their future risk on the y-axis. And you can kind of, pretty typical dividing this into 4 quadrants, and you ideally would have everything low current risk, low future risk. But as you can kind of see, they do have some places up here that have a high current risk, but also an increasing climate risk. And, what can they do with this information? Well, they can take that and build some mitigation into improving that or taking whatever steps they need to do to mitigate that future risk. Lastly, I'll just talk about something we call the Jupiter Promise, and that's trying to basically help under-resourced communities with our climate data. We've got a number of different projects in the works. Not going to be able to say too much here because I think I'm running short of time. But for example, we have a project going on in Nepal. Nepal isn't heavily instrumented and in dire need of sort of thinking about building some sort of adaptation strategies. So we provided them some data. For example, here, this is looking at, heat waves, 3-day periods above 35 Celsius and how that's going to change in the next couple of decades. Similar study in conjunction with the Nature Conservancy in Colombia, looking at the Magdalena River Basin. In this case, this example is also looking at the impacts of extreme heat and how heat is evolving in the future. Again, trying to go after helping some of these communities, these at-risk communities, these under-resourced communities build better strategies for adaptation. And finally, there's a lot going on here. These assessments, I'm vastly sort of underestimating or understating the size of the effort that goes into building the kind of things we're trying to build. Not only does this require sort of cutting edge science, cutting edge statistics and data science, but even the engineering infrastructure that goes along with it is just equally as impressive. And I'm not bragging here, but it's just an amazing team, and it's just so impressive to me to sort of see how these people are pulling this stuff off. We use lots of different data sets, lots of different kinds of data. Non-Gaussian data is typical, missing data is typical. We deal with all kinds of these issues. I can't impress enough about scalability. Even simple things like fitting a distribution to a simple set of data, something we do on a daily basis, but we don't do it once or tens of times. We do it thousands, tens of thousands, tens of millions of times. And it's amazing how challenging that simple problem actually is, to try to do things robustly and at scale. Validation, as I said, is really, really important. We can't really talk about it here. That's a whole talk by itself, but that's an integral part of everything that we do. Lots of different areas of statistics and data science that we focus on. And I guess I'll stop there.
Wow. Thank you so much, Steve. First of all, I invite everyone to mute their microphone and let us give a round of applause to Steve for this very interesting, full of so many things presentation.
Thank you.
Okay. Now, if any of the attendees wish to ask any questions, please feel free to unmute yourself. For now, we have 2 questions on the chat. Also, if you may write questions on the chat, we can read it for you. That's not a problem. Let me start with the 2 questions that we have in the chat, maybe. The first one is, for the stat modeling, do you primarily use Python? This question is from Catherine Sparrow because apparently in his data science degree is primarily using R. So if you have any question about the language, yeah.
This is yes. Okay, I'll just start by saying yes. Our almost everything that we do is in Python, but we also tend to have a philosophy of we do whatever works. So we've done things in Python, we've done things in R, we've dabbled in Julia, and working in sort of a containerized, we do a lot of things inside Docker containers. And so doing things in a containerized environment works pretty well with that. As much as I love R, and I worked in R for years and years and years and years, and all the precursors, Python right now is sort of the thing, and the software engineers love it. I curse it every day that I have to code in it, but it is sort of the standard. My advice though is just, what I tell a lot of people, especially students, is make sure you have good software sort of development skills, the basic stuff. You sort of understand how to write code, you get some experience in reviewing code, and all of those best practices that go around it, because languages are going to change and evolve, and you need to be sort of open to sort of the next thing. And so it's more about understanding those fundamentals and those best practices. And that would be my advice, or usually is my advice to any student.
Thank you, Steve.
But yes, the sad fact is Python is king at the moment.
Thank you, Steve. Thank you, Catherine, for the question. Now, August Bosch has another question. In the machine learning, you mentioned feature selection. What is your feature selection technique, or which feature selection techniques do you use there?
Well, it varies. It depends on the project, but in that particular one was a variant on just a simple forward variable selection. The detail, it's not as simple as sort of most textbook things, but it is at its heart basically a forward feature selection.
Got it. We have another question from Lelis Bravo de Gueni. Do you have she is in I'm here with my environmental statistics class. Do you have any recommendations for this grade group that's going on to graduate soon?
Man, that's a hard question, Lelis. I mean, there's so many things that I could say.
Thank you, Steve.
It's a great place to be at the moment, right? I mean, in part because there is a lot of stuff going on, whether it's companies like Jupiter, whether it's bigger companies that are hiring people into sustainability positions. In fact, I lost somebody last year, a wonderful person with a background in hydrology, but was working in data science, and went to Amazon in a sustainability position. So I mean, there are just lots and lots of opportunities out there. Lots of interest in this stuff, and I don't know. I think that's the best I could do at the moment.
Thank you so much.
Maybe you have been in both sides, in academia and industry, right? So you know how things work in both sides. Do you have any comment for that? Because sometimes the students has, this moment in life where they need to decide which road to take. So do you have any comment on that?
Yeah, I mean, I think the biggest thing that I think of is oftentimes we're after the exact same thing, meaning the research is the things we're trying to accomplish in the research are very similar, right? It's just there's a different constraint set, meaning a young assistant professor, for example, has a lot more flexibility. There are constraints on what you need to do, particularly, to get promoted and get tenure and all of that. But but it's a very different constraint set. When I moved to the lab, for example, at NCAR, it's a different constraint set. There was a different focus. And then moving to industry, the constraint set changed again. And in there, it's a little more about you're doing things under a little, the time scales change a lot, right? When you're thinking about publishing papers and writing grants, you're talking about time scales from months to years, whereas we think of time scales and do our research on weeks to months. And so that's a slightly different mindset. And the other thing is academics really want you to drive things probably further along, meaning we really embrace iterative development. On the other hand, I've had papers rejected because reviewers thought it was nothing more than an iterative development, right? So, and maybe others have as well. I mean, but we embrace that, right? Because that's kind of how we have to move things through our cycles. So it's really a lot of the same stuff. It's just done a little bit differently, or maybe a lot differently. I don't know. It depends on how you want to think about it.
Excellent. Yeah, that's right. Abdel, you have any question?
Yeah, well, I am very pleased with your presentation, Stephen. It's quite wide and covers lots of things. And I noticed very quickly that you are avoiding speaking about bias. And I think bias is at the heart of the big problem in my point of view. One of the things that puzzles me, how do you estimate the yearly global temperature average when you are talking about, different regions with different dynamics and different data collection, how they are calculating these things? I am really puzzled about this aspect. The second point that I think when you are talking about physical risk and the transitional risk, when we are doing these things, we are doing them in terms of monetary. We are talking about the money that have to mitigate the risk that is being occurring or predicted in the future or whatever direction it is. How do you take the inflation into account when you are doing this kind of risk? You see, it's if you are telling me now we are spending 10 billion, what is the value of the 10 billion 50 years ago? Or how it's going to be much later? This is an issue that need to be probably considered. I don't know.
Yeah, I'll take I'll respond to the second one first, and I completely agree with you, right? So we are just now really embracing on getting into the economic impacts, and you bring up a really crucial point, and that's what is the inflation rate or what is the discount rate and all of that. And, I think this is what drove me out of studying economics in college, right? You have to make a lot of assumptions. And when we are sort of thinking about that, that is sort of the basic idea, right? And it's subject for all kinds of debate, is you do have to make assumptions about, what is sort of that inflation rate doing in the future.
I think the aspect that I just was wondering about, because I think the inflation could be transitional as a result of the COVID-19, and then we came with this Ukraine and Russian war.
Right.
And I don't really know, how do you separate the climate from these things?
I'm not sure you can. And like I said, I think what the issue bring up is a very important one, and one that, I think we can debate to no end. The last thing I was going to say on it is I do think it's really important, though, that we do make the attempt to translate sort of the physical risk numbers, probably $2 or some other monetary figure, because that puts it in scales that the decision makers are going to pay attention to. It's easy to say a 1 degree change or a 2 degree change, and maybe from a science perspective, we understand the impacts of that. But if a 1 degree change is a 10 billion change and a 2 degree change is 100 billion change, maybe people who have the ability to make a difference will start paying attention. So I do think that translation is super important. The details and the crazy things that you have to do that, I don't totally understand, and I think you bring up in totally valid points about how it's done, and I think we'll debate that to no end. Even the paper I cited from Nature Climate Change, gave a huge range on what the overvaluation in the market is, and primarily they say that that's due to different assumptions about the discount rate. So it's a huge source of uncertainty. As to your first one, please do not take sort of my glossing over bias as any sort of statement that I don't think it's important. It's critically important. It's hard to quantify. It's hard to adjust things by. As you said, it's very different. There's not a global bias correction. There's not, there's not a season, there's not a, you have to think very, very carefully about how it's done. It's even more complicated because we're bias correcting models to observational data sets that have their own biases. So it's a bit messy, but critically important.
Well, I agree with you, and I think the interesting thing that the stuff you did about the floods and the flood risk, these are usually local problem or the hurricane that hits the United States, and we have much more accurate result for something like this. But when we are talking about the extent for the world, and the map that you showed about, it was actually connected with the Middle East, where you was indicating greater than 38 degrees. And you just have to ask how these things are calculated. You see, it's interesting. But yeah. I enjoyed your everything was great. Thank you.
Thank you. I appreciate that.
Thank you. Steve, I have one question. Most of your talk was about experiments, or what you show actually were experiments on land, and that makes sense because we as humans we live in land, right? So that makes sense. I wonder if there is something going on about studies on the ocean. If you have any comment on that.
Well, I was in a bunch of meetings yesterday, actually, thinking about trying to do some work with waves out in the deep ocean, because, and a lot of that just our focus is on places where people and infrastructure are, right, and so that moves us away a little bit. I mean, so our interest in ocean is a lot from the tropical cyclone point of view. And so understanding surge, so we do use ocean models and things like that to sort of understand, wind-driven surge up onto the coastlines, and that's a complicated modeling problem in itself. And that's one aspect. As I said, we just started some work on in the last, literally yesterday, thinking about waves and the impact of waves. That's on tap. So those are two places where sort of more ocean plays a role, is sort of understanding, surge and where surge comes from, and then now thinking about waves.
Excellent. That's great. So
it can't be diminished, the role of the ocean sort of in climate projections, right? But yeah, it's sort of indirect from what I'm doing right now. Yeah,
and probably they're going to be. I mean, I don't know if you are the only ones working on that right now, but probably it's going to be a big thing in the future.
Yeah.
as time progresses. Yeah. Thank you for all your questions. Now we are going to stop the recording, but we can continue the discussions afterwards. Please remember to visit our website to keep you update on the next speakers and events. And thank you so much, Steve. It was really, really awesome. really awesome.
Well, thank you very much for the invitation, and anybody who I can hang around for a little while longer, but if you have questions and need to lead, feel free to reach out. I'm more than happy to try to answer what I can.
Thank you.